Hello, my name is Kateřina Pavelková and I work as a research associate in ADVACAM. Today I would like to introduce you our new software called Trax Engine, which is designed to help you process data from Timepix detectors quickly and efficiently. In this video, I will demonstrate all the useful features using some real-world data examples. To capture your own data, you can use Pixet software. But don't forget to load the right configuration to capture energy-calibrated data. Configuration file is available on the USB drive, including in the detector packaging. Once the Trax Engine is launched, the user interface will appear. It is divided into graphical section with several tabs and processing control section, which allows you to load the data or perform filtration. First, we need to load the data and the calibration matrices in the General tab here. I will show a real patient data that maps secondary radiation present during proton radiotherapy. The detector was installed on the ceiling of the treatment room and operated in data-driven mode, which enables to capture every single particle. You can upload several files at once. The corresponding calibration matrices can be downloaded from Pixet software in the detector settings. To upload them, just select the folder, which includes 4 text files containing calibration matrices A, B, C, and T. The next step is to set an appropriate sampling time. This value will serve as the time interval over which the software calculates dosimetric quantities, such as particle flux or absorbed dose. I will set 1 second. Below, you will find parameter settings related to an automatic selection of suitable particle identification algorithm, based on which detector configuration you are using. I will select the right chip type, which is Timepix 3, sensor material, which is silicon, its thickness, which is 500 micrometers, and bias voltage value applied during the measurement. Now we are ready to start the processing. The processing went fast, we can already see the results. In the input data, there is 2000 particles, and the total time from the first to the last event is slightly more than 79 seconds, which means we obtained 80 time samples with a sampling period of 1 second. In the General tab, in graphical section, we can gain a general overview of the data. This color chart shows measured particle count over time for each particle type. We can see there the irradiation profile during a single treatment fraction. To see some details, we can easily customize the figure. We can zoom in, navigate through the graph. If needed, we can always go a few steps back or restore the graph to its default. Then we are also able to configure the subplot layout here or change the properties of axes and curves. The customized graph can be saved by using the Save icon. The plot on the right visualizes the radiation field detected as the amount of energy deposited in individual pixels. We can see their particle tracks, also referred to as clusters. This input field allows us to enter different number of displayed particles. I will type, for example, 300. We can notice that the tracks are oriented in certain direction, which means that the sensor was oriented at an angle with respect to the radiation source. We can also display the energy in logarithmic scale or switch to the following 300 particles. The histogram below can give us an idea about particle properties. These properties are called cluster variables and can be selected from this drop-down menu. Detailed description of all the cluster variables can be found in Trax Engine user manual. For now, I will select energy spectrum. I can switch between linear and logarithmic scale on both axes and change the number of bins. Next step, called histograms, allows you to easily compare two cluster variable histograms. I will choose energy histogram and compare it to a histogram of linear energy transfer. It can be observed that these histograms are quite similar. I assume that this peak originates from protons scattered within the patient's body. Next step provides a detailed cluster analysis. We can, for example, select first 100 particles, and then we can list through them. We can focus on different shapes of clusters and their energy distributions. For example, these 1-pixel clusters originate from photon interactions. This one is a nice example of proton which was incident on the detector at a nearly perpendicular angle. This could be a track generated by the energy deposition of an electron, likely recoiled from an interaction with a higher energy photon. Next step allows us to perform detailed time evaluation of dosimetric quantities. The top two graphs show particle flux over time, and the bottom two graphs show dose rate. It is possible to perform the analysis either for all particles at once or separately based on their type. The following tab summarizes the output of automatic particle identification algorithm. This algorithm is based on neural networks and is able to sort the clusters into 3 particle groups: protons, photons and electrons, and ions. We can set higher cluster count to see more particles. The majority of clusters is usually generated by scattered photons. Next, we can see the protons that have entered the detector at an angle. There is also one heavy charged particle identified as ion. The above charts are useful for a separate analysis of cluster properties and time profiles across different particle types. The next step is designed to display the output of cluster filtration. Filters can be configured in the Filter tab on the right. For this example data, our goal will be to filter only the protons and visualize their properties. Protons differ from other particle types by their large size. So let's use this to filter out small clusters induced by photon interactions. I will set the minimum cluster size to 20 and click Apply. We can see that 500 out of total 2000 clusters passed. If we display more clusters, we can observe that high energy recoiled electrons are also present alongside the protons. It seems that we will have to adjust the filter criteria. For example, we can try to set the minimum track thickness to 0.1. I think this works well. Here we can list through the individual proton clusters. The above charts will now display only the properties of the filtered photons. Maybe we can switch to filtered out particles to check whether we have accidentally excluded any of the target particles. Everything seems alright, because this display contains only photons and electrons. If you decide to apply the configured filters in future processing, just mark this checkbox to enable it. The difference is that you will be able to export output files containing only protons. I will show you how to do that later. The next step provides directional analysis based on spatial vector defined by the first and the last detected pixel signals of each cluster. It is obvious that the significant number of particles came from a 45-degree angle. It is possible to analyze either the azimuth angle within the xy plane or elevation angle alongside z-axis. On the next step, it is possible to perform more advanced analysis, such as analysis of coincidental events. The last step is intended to visualize spatial maps of the most important quantities and cluster parameters, such as cluster count, energy, high, meaning highest pixel energy within a cluster, and cluster size. Now, after the visual data inspection, it would be suitable to save the process data into output files for later analysis. To do that, let's return to the General tab on the right. Then, check Export Data, select a directory, and click Export. Now, the output files containing all the unfiltered clusters will be saved. Let's have a look at the output files. These folders include event visualizations, histograms, spatial maps, and much more. For advanced analysis, you will probably appreciate folder named File, which includes lists of clusters together with their parameters and list of time samples with dosimetric characteristics. I hope this video will help you, and data processing will become faster and easier with Trax Engine.